Let's clarify the second part of this lecture. So the idea is that what to choose niobium diselenide as an example, because this material has a lot of interesting properties already, and this is the reason. And the interesting properties include, first of all, this so-called icing superconductivity. The feature is basically that the in-plane superconducting field can be very large, exceeding this so-called Pauli limit, which I will explain throughout this talk. And also the so-called almost metal phase or quantum metal phase, which also shows up in disorder superconductors in 2D. But here, since it happens in the crystalline system without disorder, so this is why it becomes also interesting. And the other feature is the so-called quantum Griffin singularity. And this one I will not cover. So just if you're interested, you can also go through this literature and find what this one is about. So the basic idea is that there is a transition from superconductivity to some normal state. However, this transition is not a single point transition. And so if you see that for different temperatures, if you sweep the B field, the transition, the crossing point of these curves, they move toward the higher magnetic field when you cool to a lower temperature. So this is a basic feature. People call this quantum Griffin singularity. Why I'm not talking about this is because now people also find this in the 3D superconductor. So this is not just limited to 2D. Probably because 2D is just easier for tuning. So this is the idea. But before I talk about niobium diselenide, I want to also mention a bit about the some latest development, because as I mentioned that this is for attracting even younger people like me to join this field. And for these are like the new, really new developments in this field. I think a lot of attention has been gathered toward these around these twisted graphene, and nowadays it's also about the so-called Lombardizo graphene, which is a special stacking way of graphene. So usually graphene you have this Bernoulli stacking of AB. But now this is different. This is so-called ABC. So then, because of the stacking, then you have some kind of flat band, and because of this flat band, some interesting physics happens. And in this recent paper by this MIT group, they observe superconductivity when you apply some displacement field. And there are several superconducting states. They call this SC1, SC2, SC3. And within this SC1 state, around this point, when they measure the Hall resistance by sweeping the field, you can see that it shows some of statistics. And when you cool down, you still see some kind of jumps around this corrosive field when it's already in the superconducting state. So this is why the system becomes quite interesting. I think it matches several requirements by John, if I pronounce correctly, in this morning. That first of all, it's a 2D superconductor. Secondly, it has some kind of ferromagnetism, so it shows that it could be spin triplet pairing, and thirdly, it's superconductor. So with these features, people call this or the signatures for chiral superconductivity. So I think that, yes.
So actually, the difference between this and biolographene is the biolographene, you have this magic angle and you have the AB domain aligned. And here you say that you have a multi-stack with 3 different alignments and then you repeat the structure.
Yeah, here I forgot. So because I want to just quickly go through this, this is a 4-layer graphene. 4-layer and ABC, and the other one is another stacking along this way. ABCA, yes.
Why is it called chiral?
Because it has ferromagnetism, kind of ferromagnetism. So the people are saying maybe this is for the spin channel, it's a spin triplet, and then the orbital channel could be px bar IPY. So this is just the proposal. So this is one thing recently going on. The other one is also about twisted. People move from twisted graphene to something else, like twisted this tungsten diselenide. And I was quite amazed by this because I was working quite a lot on high temperature superconductors, cuprates. And when I looked at this phase diagram, this was like a dream for high temperature superconductor people, because with one sample, you could tune these parameters and they can go through the whole phase diagram just within one sample by tuning some voltages. So you can see that this phase diagram looks pretty much like high temperature superconductor with this antiferromagnetic phase, and then you get the superconducting dope, and also you have some strange metal, and then you have higher doping, you go to this Fermi liquid phase. So this is also quite interesting. And the third development in this field, I think, is about nickelate. This is not particularly 2D, but they have to do a 2D because this so-called 3 to 7 compound, in the single crystal form, you need to have a very high pressure, usually 20 gigapascal, to make it really superconducting. And the transition temperature onset TC could be 70K or even higher. And another way to mimic the effect of pressure is to grow this film on a substrate. The idea is that when you grow this very thin film on a substrate, you have the strain effect. This strain effect is just like the pressure. So that by growing this thing around stream in the cell, then you can have the right pressure effect, so that this system also shows a relatively high TC for this system. So this is also, this is very thin film, so this is really 2D. Okay, so 3 unit cells. So each unit cell is, let me see, I don't know the number, but I don't think like 3 or 2.
In order to get this, you would need a large mismatch.
Yes, exactly.
Depends on the mismatch.
Yes. So the people, what they do is they really screen a lot of substrate and then trying to find the right one for providing this pressure.
Different substrates.
Different substrates.
Just because I don't remember this paper exactly, my memory, superconductivity nickelate was happening only when it's really thin. Is this film a bulk with pressure, or it's also a film?
Oh, this is just thin film. Without
it's
pressure.
Still a thin film. Okay, but it's not still a superconductivity in bulk, even with pressure, right?
It's this one. Okay, so this 3 to 7 single crystal under pressure is a superconductor, and then they grow thin films in the same structure, and then they can have the superconductivity. So these are some latest ones. Then I go to niobium diselene as example, and I want to cover some effects like two-dimensionality effects as in superconductivity along with metal phase, and then I move on to something. I changed the title when after this morning session, I rushed and changed this from 2D superconductors and topology to 2D superconductors with topology, because apparently these things are not really topological superconductors. Twisted cuprates, if I have time, I'll touch upon this. This is predicted to be a topological superconductor, but this is still under debate. So, niobium diselenide. A lot of people in the audience, are experts on this on this topic. So, niobium diselenide has this single crystal with a hexagonal shape. When you look at this crystal, and it's called this 2HA stacking. So there are two different, typically two different stacking, 2HA and 2HB. So 2HA means basically when you look from the side view, the niobium atom aligns with the niobium atom in the other layer. So this is the kind of stacking. But you can see that the orientation of this selenium layer is different from the other one. So within a single layer, actually it breaks the inversion symmetry. So you don't have the central symmetry within a single layer. And this system has a TC of 7.2K. And also it has a charge density wave around 3 Kelvin. This is pretty established. So for this particular system, the idea is that this is a layer system, so one could really exfoliate and then really go to the mono layer. So the band structure looks like this. It's a kind of complicated band structure with essentially a whole band around the gamma point, another bigger whole band also around the gamma point, electron band, and also another whole band around the K point. So this is essentially for the bulk albumin diacylate. So here, I think this it depends on the calculation. Some calculations show there is like kind of exchange crossing, but not really in all the calculations. So essentially, I think for experimentalists, we just trying to think this system has several hole bands and several electron bands. So this is, I think, sufficient. And also around the K point, which we will mostly focus on, it's the hole band which is the most important band. For this system, it has charge density wave, and this charge density wave is also kind of under debate. The mechanism for the charge density wave is still under debate. So the Q of this charge density wave is roughly 2/3 of the distance from in the Brownian zone from gamma to M point. However, it's not really exactly 2/3. There is a very small percentage of deviation from 100% to 2/3. And from the neutron scattering, also people saw this. But the exact reason for this is, I think, not really well understood. They just observe this phenomenon. And from STM, people also see directly these charge density wave. And the charge density wave basically means that along the lines of the atoms, this is just selenium atoms that either every 3 atoms you have one brighter atom. So this actually corresponds to somehow like 3×3 CDW. So it looks like commercial rate charge density wave, but actually it's not. So from STM, it looks always like the commercial rate. People just argue that you have some incommensurability just around the boundaries of this. And also the charge density wave has 3Q. So this is just one direction. This red arrow shows just one direction. It has also the other 2 directions. So these are the basic understandings for the charge density wave. So then we go to thin film. So before this work, people also try to exfoliate, but the idea was for albumin diacylate. At that time, people realized that the exfoliation works similarly as graphene, but then you cannot do it just in air because this system can degrade, the material can degrade very fast. So what they did is just exfoliate everything just in the glove box and also try to cover this whole thing with boron nitride, and then you can protect the film. So then back then, in Kim Mark and Jason's group, they exfoliate down to a molar layer, and you can see that the transition temperature goes down with the reducing of the thickness. So this dimensionality effect, they argue that when they plot this as a function of the number of layers, then this matches quite well with this formula for the weakening of interlayer Cooper pairing. So you have less layers, so then the interlayer Cooper pairing becomes weaker. So that's why TC becomes lower. This is the idea. And then people just around the same time. Actually, this paper appeared before, so they first tried some optical measurements, which was experimentally, I think, easier. And then they measured the charge density wave. In the Raman spectroscopy, there are some features here and here, and these features correspond to the charge density wave. I think one way experimentally is that these features just disappear when you increase temperature above 33 Kelvin, above this charge density wave temperature. And this one is well established that people observed that quite some time ago in bulk albumin diacylate, which is corresponding to the so-called amplitude mode of this charge density wave. So the amplitude gets excited at this particular frequency. This mode they didn't understand at that time. However, it also disappeared around the same temperature. So then they call this also CW related. So one can see that these features, they can extend to much higher temperature when we go to, for example, bilayer, and for molar layer, and it goes to even higher temperature. Also, although I would say that by looking at the data, I cannot really so confidently say that this can really extend to this high temperature, but you can see that at least it's enhanced from bulk to a molar layer. So this is why they plot this phase diagram by saying that when you reduce the number of layers, then the transmission wave gets enhanced. So this is also about the dimensionality effect. However, just around the same time, this is also in 2000. This is 2016. So people observe this is from Stanford group. They grow this by MBE on a special substrate, which is bilayer graphene. So you can somehow carbonize this silicon carbide substrate so that you end up having 2 layers of graphene on the surface. And then this is a pretty flat surface. With this surface, also with van der Waals bonding, so it's very easy to grow. You need to try, but still comparably easier to grow the niobium diselenide. And by doing so, they could realize a smaller layer, and the TC is roughly 0.5 K. And they claim it's opposite to the other one. So from the exfoliated samples, the charge density wave is enhanced. But here, from STM, they directly measure STM that they observe that the charge density wave only appears below 25 K, which means that, for example, in the picture in the middle, you don't see these brighter spots for every 3 atom. But then you see this only at 5K. So apparently there is something like contrasting each other. So I also talked to the one of the authors, Xiaoxiang Xi, just recently, and he thinks this is still not really clear. But I think from his experiment back then, in 2016, there is some hint. Maybe it can explain a little why. So what they are doing in this paper is that by going down to a monolayer or bilayer, so now you have not so many carriers, so that you can tune the sample easily or relatively easy, so that they can use this ionic liquid gating. So the liquid gating can offer you a large tunability in the terms of, you can see here, it's roughly 10 to the 14th per square centimeter. So by doing so, you can tune the TC in a larger range. And especially here, they measure the Hall effect, because I forgot to mention that for the charge density wave to appear, then it reconstructs the band structure, so that then you have from kind of Hall dominated system and turns to a more like electron dominated system. So there is a bending point just around the charge density wave, and they argue that this bending point somehow shifts. When you apply the gate voltage, it shifts to lower temperature, and essentially it cannot be seen and becomes comparable to niobium disulfide. And niobium disulfide has no charge density wave. So they argue that by inject a lot of electrons into the system, you somehow suppress CDW. So I think this is consistent with this picture, so that when you grow niobium diselenide on graphene, actually graphene can transfer a lot of charges, electrons, to your niobium diselenide. So that's why the TC they observe here is lower than exfoliated. The exfoliated one here. Here is 3K for monolayer, but when you grow this, you get only 0.5K. And then because of this doping effect, the charge density wave also gets weaker.
Again, about the mismatch. I mean, how do the graphene and the niobium diselenide, how do they match? And maybe that's
that's a very good point. So for this particular, so the people argue that the graphene is pretty flat, so that niobium diselenide does not. You don't need to have a lattice match. So it's like van der Waals bonding between them.
That doesn't depend on the matching.
It doesn't depend, right? Doesn't depend on the match. That's for this.
The graphene and the 1.3 application of investigation.
Yeah. But from this STM, I think they I have to double check, but I think they say there is no strain effect in this. So if one grows this on, for example, STO or other substrates, you may have some strain effect. But you are sure right, so strain may play a role.
In the experiment with the ionic liquid, since niobium diselenide is so sensitive to chemistry, can you really?
Yes, exactly. So this is also one thing. So at that time, everybody was claiming that this is a purely electrical effect. And after so many years, people already aware that there could be intercalation chemical effects. So at that time, here in their paper, they claim they protect the niobium diselenide by molybdenum disulfide, so that to reduce or to eliminate the chemical effect. However, I think just from the tunability here, this is very high. This is 3 to 10 to the power of 14. For this tunability, you need really like without the capping, without molybdenum disulfide, you can have this. So by seeing this large tunability, actually tells you that it could be some kind of chemical process. So exactly what the process could be is the hydrogen atoms, protons, could get injected into the sample, and that donate electrons into the system because protons are so small, so they can go through molybdenum disulfide. This is just my speculation, not really proven.
Earlier, long time back, there was some observations that selenium could easily escape from the niobium diselenide surface. Selenium atoms could create vacancies. Is it possible that this can be a mechanism of the fact that we can have electron doping, and so this disorder of selenium adds to the suppression?
That could be. I think in their paper, they're trying to claim this is electrostatic by showing that this is, for example, the scaling effect is kind of linear, and also it's reversible. That if you really dissolve selenium, then it's not reversible. So let me just move on. So this part is, and let me end this part by showing you another interesting thing about the MBE grown samples. So at that time, also in Tsinghua University, my colleague, they grow this niobium diselenide also on bileographene. And what they actually did is when they kept the same system, because they know that for monolayer is very easy to degrade. So they kept this with silicon, with just amorphous silicon. And when they do this measurement after, when they take out the sample measure, they see that the TC is pretty high. It's like 3K or 4K, much higher than what the Stanford group reported. So then they started to investigate this thing and realized that silicon can actually do something to the niobium diselenide. So in the STM measurement, they show that by just dope some silicon on the surface, just evaporate some silicon on the surface, then with the coverage of silicon increasing, the superconducting gap first increases and then decreases. So and silicon does not donate any electrons or holes to the system. It does just increase the disorder. And the similar things happens for sulfur. So when they grow this thing with a mixture of selenium and sulfur, and then they see that the TC of sample goes up first and then goes down. So this is kind of interesting. And then they claim, the idea is that why this happens is they call this multifractal fractality. So which is somehow related to some complex physics dynamics. I think still they cannot really fully answer the problem that could be that these tokens, although they do not transfer charge, but they can destroy CDW. So by destroying charge-emitting wave, you could increase for enhanced TC, enhance the superconductivity. Because if we assume superconductivity and charge density wave, they are competing with each other. You suppress one, you may enhance the other one. So this could be a wrong effect. However, this cannot explain why people before observed that when you transfer charges to the system, both the charge density wave and the superconductivity get. So I think there's still something ongoing with this. So, but the take-home message here is that MBE grown sample could be interesting. Maybe from the exfoliated.
Do you have a sort of understanding why charge density waves would suppress superconductivity, or what would be the mechanism?
I would say that just naively speaking, the charge density wave and superconductivity, they both take the same amount of charges. So like charges, they need to do one thing. They have to choose. Either they go to charge density wave or they go to superconductivity. If all of them go CW, then there's no charge to do pairing. So in that sense, I think they are kind of competing. But this is one way of thinking this. I think some people also argue that CW comes from electron-photon coupling, and electron-photon coupling can also help superconductivity. So they are actually enhancing each other instead of competing. So I think for naive density, this is still quite under debate.
The energy scale of the CDW is much higher.
Yes, much higher.
Yes. In tens of K.
Yes.
In a way, it should be an order that is much more dominant, and it's going to set the rules. And then the superconductivity is going to leave with whatever the crumbs are left on the table after the charges they were rearranged.
Yes. Yeah.
That's something that also an opinion.
Yes. Yeah. Exactly. So I think let me see that. Many of these things I just try to express my simple view, and so please feel free to interrupt and also we can discuss. So now about acting superconductivity. So this is right in this first paper about this 48 single layer. Let me start with what the icing comes about. So we know that in order to break the Cooper pairs, you have, roughly speaking, two ways. One is that you can break it by applying the magnetic field to induce vortices. So for type 2 superconductors, for 2D superconductors, they are just type 2. So when you apply sufficient high magnetic field, you just break the pairs. But if we ignore that effect, we think about the Zeeman effect for the Cooper pairs. The simply picture is that because you just rotate the spins to align with the magnetic field for the this spin up and spin down, they align in the same direction, then they can appear in a simple singular pairing picture. So then considering about the energy, so this is the energy difference between the normal state and the superdynamic state. And then if you add this Zeeman splitting into consideration, this part comes about this Zeeman energy. And by matching these two energies, then we can end up having a relation between the gap and the magnetic field, which means that at certain magnetic field, then the normal state actually becomes more favorable than the superdynamic state. So by combining these two equations and also by using this standard BCS ratio about gap and TC, then we can have a conversion between this magnetic field or the this is the B, and together with the TC. So this gives us the so-called Pauli limit, which is roughly 1.8 or 1.8 or 2 times TC. And that means that if we have a 2D superconductor with a TC of say 3 Kelvin, then when you apply an in-plane field of 6 Tesla, you should be able to suppress superconductivity, Q superconductivity, which is not the case in niobium dicene monolayer. So the magic happens for niobium dicene monolayer. These are the band structures calculated. So down to a monolayer, it looks pretty much like niobium. So these bands are mostly just from niobium. And now the band structure becomes quite simple. You have one whole band around the gamma point, and then another whole band around the K point. And it's just focus on the band around K point. For some reasons, people argue that the band around the gamma point doesn't do much. So then we focus on this band. And for this band around K and K prime points, and now I'm drawing this around K and K prime points. I mentioned before that this crystalline structure lacks the inversion symmetry, which means not really the like for Rashba effect, we have this mirror symmetry thing. So here is the central symmetry. So if I draw a line connecting one selenium atom, trying to connect that selenium atom to go to the other side, you see that this empty circle cannot match with the real position of selenium. So it lacks the inversion symmetry. So due to this breaking of inversion symmetry in this monolayer, then the spin orbit coupling effect for the K and K prime points, they are opposite. The strength is the same, but the direction is the opposite. So people argue that due to this spin orbit coupling effect, then the spin splitting around the K point, let's say that the spin down is moving down and the spin up is moving up, then the opposite happens for K prime points. And now, after considering the spin orbit coupling, then the pairing happens between K and K prime point, K and K prime points. But the spins here, for example, the blue one pairs with the blue band pairs with this red band. But the spins now they are locked because the spins already you have a sigma splitting due to this spin orbit coupling effect. And the direction of these spins are pointing in real space out of plane. So due to this so-called spin orbit coupling induced spin splitting, we have the spins somehow losing the degrees of freedom. So they are locked just in the z-axis. So this is why we call this icing pairing. So because the spins are just in one, it has only one degree of freedom. So with this, then how to understand? So we can try to understand this largely enhanced upper critical field. So people observe that the upper critical field could exceed the so-called the previously we explained the Pauling limit, which is just this in the reduced plotting, just 1, and it can exceed this Pauling limit by a factor of, from the experimentally available magnetic field is about 4, but if you extend that, it can be even 6 or 7. So how to understand this? When you have a spin, when all the spins are just locked out of plane, you try to apply the in-plane field. This in-plane field cannot rotate the spins. And also the in-plane field cannot induce vortices because it's very thin. So in this case, then because of the spin locking effect, it's very hard to polarize the spin. So it's very hard to kill superconductivity. So this is the idea behind the icing superconductivity.
This high field exceeding the Pauli limit is not specific. I think it's predicting.
Exactly. So for some other systems, you can see also the very large upper critical field exceeding the Pauli limit. So it's not necessarily the case. So in our case here, I would say we know the back structure quite well, and for back structure, it matches this is interpretation for this this observation. But this, I think, it's becoming more and more consistent because when people change the material, for example, changing niobium diselenide to tungsten disulfide, which has the atom becomes heavier, then you see this effect becomes stronger because the spin orbit coupling is stronger. So the Z-mass splitting becomes stronger. So in that sense, it's kind of consistent. Also, trying to argue, people also observe that when you go to bilayer or trilayer, then this effect becomes weaker. The reason is because when you go to these thicker layers, then this inversion symmetry effect, this inversion symmetry breaking effect, it becomes weaker. In each layer is still inversion symmetry broken, but in the total system actually preserves the inversion symmetry.
So may I make 2 comments here?
Yes.
First comment is that in the presence of strong spin-orbit coupling, singlet and triplet is not a good quantum number.
Exactly. Yes.
Perhaps you were going to say that.
Yes. Yes.
And so you naturally get a component of triplet pairing which is highly insensitive to the magnetic field. That's one comment.
Yes.
Second comment is that with Ising spin-orbit coupling alone, theoretically, the Pauli limit could be exceeded by an infinite amount.
Oh, yes.
So the fact that it's finite is due to some rush buff, which is much smaller than the Ising superconductor.
Okay. Yeah. Yes. There could be some rush.
Yeah, comment. I mean, we had a recent PR 16 ago, and it's not due to Rashba.
Okay.
They neglect the gamma band, and the gamma band does produce, it does expect a finite.
So there is some other spin orbit coupling?
Well, it's need to take into account the gamma.
Okay.
And that gives you the finite.
But you do need something beyond Ising. That's yes. That could be.
That's not the whole story. That's what I mean.
Yeah. Yes, you're right. So with just the purely Ising, then it can be infinite. Yes. And I think when people put the real numbers in there, then about the spin orbit coupling strength, then you could also have like a limited value. And the rush bar, I would say for niobium, for the other some other systems, people really go to very high field because Ising superconductivity predicts some kind of upturn, but it's not really observed in all these systems. So that could be, people argue that this rush bar effect that brings your upturn down. Yeah, so I would say the Ising superconductivity up to now is just very simple, very simple understanding, or trying to understand from the pictures from some very basic models. So after that, I think, for example, like beryllium disulfide, other systems I mentioned here, tungsten disulfide, these are more heavier atoms, and the enhanced apocalyptic field is much higher, so 10 times or 15 times higher of the Pauli limit. Of course, there are some other systems. The actually, I would say they do not follow this standard understanding of Ising superconductivity, but they also have spin-orbit coupling. And the after the first measurements, just for standard, just transport measurement, resistance measurements, the people also try to see how the gap of the system evolves. We have our organizers also as experts on this. So this paper, they measured the tri-layer niobium diselenide, and then they compare this with aluminum. So what they try to claim is that by applying an in-plane magnetic field, the superconducting gap closes, but it's evolving with the in-plane field in a continuous way, and which it looks in their plot here. So looks pretty different from the aluminum field, thin field. So aluminum thin film, you have like a first order transition, and when you have the enough Zeeman splitting, you kill superconductivity, and suddenly the gap closes. But which is not the case in the niobium diselenide. So this feature is also claimed to be related to Ising superconductivity. So basically, I would say that you continuously rotate the spins, so that suppresses superconductivity. So yeah, this is another feature people claim. So then, yes, so our Clear and Hadar also carried out these measurements down to very high field, and then they observed that like what he just mentioned, this is very sensitive to the in-plane field. So when you apply an in-plane field, then the spins start to tilt, and then these tilted components, you can think of this as a spin triplet channel. So from this experiment they measure for bilayer, indeed they see that by using the standard Ising pairing, it cannot follow this very nicely, especially in the high field range. Only if you add this spin triplet pairing to consideration, then it can describe more easily how the gap evolves with a strong magnetic field. So these are the features, and also these features have been, for example, the large in-plane field. There are other features that people also try to measure in other systems too. So somehow now I think these are the features you need to, if you want to prove your system is somehow like Ising superconductivity, you want to measure these features. And then there's another development in the field that now we start to rotate the magnetic field in the plane. The idea is that to see if this is symmetric, or if you have some kind of anisotropy. And this group, they did two things. First, they measure the resistance, they measure the apocalyptic field, actually not just sitting around the superconducting transition. So this sample has a transition, one can see here that it starts to show superconducting transition around 4K, reaches 0 around 3K. And so in between this range, you have the superconducting transition going down, but when you rotate the magnetic field about 8 Tesla, the resistance response is anisotropic. And when you plot this in the polar coordinate system, it looks like a twofold like a peanut structure. So, I mean, niobium diselenide has a triangular lattice or hexagonal lattice. So this twofold symmetry is not following that triangular, following your lattice. So this is why people think this is also kind of weird and maybe related to something about Ising's conductivity. Also, they move on to measure the gap as an in-plane field. When you rotate the in-plane field, here one can see that this is deep in the superconducting state. And when you, for example, here these two features, you can apply the field either with the in-plane field with angle of 45 degrees, or you can rotate another 90, add another 90 degrees to 135, and the response is quite different. So when you have this at 45, you apply the magnetic field to 9 Tesla, you can suppress these features very easily. But if you rotate another 90 degrees, then these features, they stay up to 9 Tesla.
Just note that in this particular study, they were tunneling through chromium-bromine 3.
Yes.
Which imposes its own order, and
so,
there was an argument around that. So I don't think there's the clear evidence that what you say here is completely originating from Newton. It's sitting on a magnetic material.
Yes. So I also asked them. So I think they claim there was no special thing in this magnetic or.
Yeah,
I guess maybe at that time.
What they're saying. Yeah, my humble opinion about it, what magnetic rotation.
How do you experiment? Why are you getting a peak in
the tunneling contact?
Yes,
it's like an array of sort of it's a low Z measurement. I think. Not strictly tunneling. It's an array. It's an array of coupling. Like
so this insulating, this layer is not insulating.
It's a very thin tunnel barrier. So the Z parameter in the BTK is small. Close to 1.
These things sometimes appear. You understand the dip that you have at 0?
Oh, this is from entry reflection. So you have this.
Exactly at 0.
This one.
Yes.
So this is a gap. So then you have some kind of dip. It depends on Z and T. So if you have purely and reflow, it's just a single.
There was also just around this paper, there were several arguments. One of the arguments was that to see a C2 symmetry, one very easy way to see it is that your placement of the sample is not strictly parallel to the field.
Oh yes, I
will
mention
extremely cautious with your compensation and people. They had various. They're very long text that they wrote in their supplementary that explains why they're right. I don't know if I was right that, but.
Yes, so when they showed up this, I was also very suspicious about this because they just blew the sample. They didn't really have like a 2-axis rotator to align this.
No way to compensate.
Yes. So I have this. Okay, let me finish this and then I go to these trivial effects. So another group, they go really down to a monolayer, and in the monolayer they just measure how the resistance responds with the in-plane field, also in the transition regime. And then they claim to see that claim around 90% of the transition, then you have some kind of very weird pictures. So that it looks like some kind of 6-fold symmetry plus some 2-fold symmetry. If you plot this response just in the polar coordinate system, and then if you go down to lower temperature, so roughly 50% of the transition, then it becomes more like 2-fold symmetry. So there's
the y-axis on those plots?
The y-axis here, this is the TC, which is actually just the temperature here when you go to 90% of the resistance.
So it's 2-fold symmetry rating. Is it the same every time you cool down, or the axis can change?
So here, I think for different. Okay, I don't know. I'm not sure if they carried on this.
And is that 2-fold axis somehow locked to one of the crystalline directions?
No, I think it's not.
It's not.
So now the trivial effects. So as experimentalists, we need to be aware of this. So ideally speaking, right? So you have the in-plane field. You have your sample plane also just parallel, exactly parallel. If we have something, suppose like tilted against this parallel axis, then you can have the autoplane component of the B field. And suppose now if I start to rotate, like my pointer here, I rotate this thing to the 90 degrees. This is still fine because now all the plane, your sample plane is parallel to the magnetic field. If I keep rotating to the other side, then the autoplane component actually changes the direction. The autoplane component appears again. So then you see that if I rotate the whole full circle, then the autoplane component shows up twice. So that can, in principle, give you the twofold symmetry. However, in this, okay, there's another effect also, a trivial effect, which people just recently argue. So when you apply the in-plane field, even if it's perfect in the plane, there is a current. And you have like a sample with a fixed source and drain, you apply the current. The in-plane, in this case, the in-plane field is just perpendicular to a current. Then you have a Lorentz force for the vortex lines. So that Lorentz force may drag your flux lines out of plane. So that can induce some dissipation. And now if you rotate the magnetic field so that the field lines are parallel to a current, of course, you don't have the Lorentz force. So then again, you have the twofold, something twofold, because you rotate just perfectly in the plane with a full circle, but you have 2 times this effect. The Lorentz force reaches a maximum 2 times. So this can also induce some kind of fake twofold symmetry. I think for the monolayer case, I would say it's really hard to imagine that the flux line can really have such a strong effect when it's monolayer. But for thicker films of thicker flakes, for example, the first one. So here they have several layers. This is like tri-layer. Yes.
Is it possible to have a flux line running through the thin edge of monolayer? Because I mean, flux is rather extended. Yes, it depends on the material.
Yes, exactly. So if it's just a monolayer, I would say it's really hard to imagine how it just goes through. But for several layers, a tri-layer, bi-layer, then you can go through.
There's another effect that sometimes people talk about, that these 1D monolayers, they're never really flat.
Exactly. I mentioned this too. Yes, exactly. So this effect also nobody mentioned that so far. I think I haven't found any literature, but I know people, some people working in this field are talking about this effect. Yeah, and they're trying to prepare some papers on that. So these 2 effects, I would say, if you think about it more quantitatively, actually, both this one and the next one, they give you sine theta, this dependence. Because the autoplane component is just sine theta. But in this paper, what they observed is sine 2 theta. So then they argue that this does not follow the trivial, the effect of the expected trend for from the trivial effect. And they also demonstrate that if they intentionally tilt the sample a bit with a misalignment of 7 degrees, then they can not see the sine 2 theta dependence. Now it becomes really the sine theta trivial effect. So from this, they argue this twofold symmetry is not really the trivial effects I just mentioned. However, I think maybe there are some tuning parameters that we may not really. Maybe this trivial effect is not just that trivial. We need to have something else. However, if we really be serious about this twofold symmetry, then they propose that then that means the pairing order parameter can be is not just pure S wave, because S wave just isotropic. Then you need to have something to have this twofold symmetry. So either it's S plus D or S plus P. So then somehow I see if it's really something P wave, it goes in line with the triplet pair, spin triplet pair scenario.
That's something that will show up in velocity also.
Yes. You mean there's no nodes here?
There's also less.
Yes, maybe.
It's not You don't have a resolution there. It's,
or specific heat.
Yes, yeah, specific heat, but the sample is too small for this. So far, I think from the tunneling spectroscopy, the best data is from Clear and Hadar, and it's very nicely S-wave gap, I would say. So there's no.
It's also pretty hard to say because also there we weren't perfectly tilted as well, and so the data will take it 1.2K, not in a dilution.
Yeah.
We already expect.
Okay. So that's something we still need to do.
I think we have to convince the people in Grenoble to give people more magnetizers.
Yeah, so I will say that so far let's take this data with a grain of salt. So there could be something else explaining this. So this is the strain effect I want to also mention, that be aware that so far all these experiments, we put the contacts on the bottom and then you transfer the flake. So the flake is never flat. So look at this picture that when they observe the six-fold symmetry, you see that there are so many contacts, and these contacts really can disturb the flatness. And some people tell me that if we have different alignment of the contacts, you can actually induce different
contacts can also disturb flatness if they come from the top. Not only from the bottom,
okay.
they strain, and sometimes you do it cross-sectionally, you're actually folding up the material. So once your reference is a single atom, it's really, really hard to stay flat on a single atom.
Yeah.
So it's,
this is something we all need to be aware.
It's a graphene maybe.
Yes. Always copying or.
Are there experiments where there are non-conductive flakes?
For
magnetic experiments or
I'm not aware of.
I guess very hard experiments.
No, but maybe you want to embed the material inside a resonator or something, so you don't actually physically touch it. Yeah.
The resonator does the same problem, I guess, because the
HBN sandwich, and HBN sandwich can give you a pretty good strong anchoring.
Yes.
As long as nothing touches it, nothing touches it.
Yeah, always these encapsulated samples with H contact if people can do it. I think nobody has done that now for niobium diselenide. To have the encapsulated sample as with somehow like graphene to have H contacts.
People do H contacts, so increase the should be. You guys do H contacts, no? On MBSC2. H contacts on MBSC2.
Side contacts.
Side contacts.
Yes, I think so.
Yeah. So
that's not what I do. Others.
You can ask it.
Just be a little bit fast. So the other thing people have seen now is, I think this is for me, kind of interesting because at that time, I think all people, many people are focusing on single layer or ultra-thin films because they think that only in this ultra-thin case you can have interesting physics. However, this paper shows that it's not necessarily so. So you go to its thicker films. For example, here it's like 25. This one, 20 nanometer, 22 nanometers. And then they observe some kind of upturn in the upcritical field. Of course, this feature is not so pronounced. However, they also observe something else. For example, that when they rotate, so this upturn, they claim is related to this FFO state. So let me just quickly go through this. So FFO state in the classical case is referring to this situation that you have again the Zeeman effect that splits your bands, and then when you have really this large Zeeman splitting, then the spin up and spin down they cannot pair because they do not have the same formation. However, FFL argues that or people argue that you can have a small section around on your Fermi surface that pair with finite momentum. So this is why this is interesting. So because of this finite momentum pairing, then instead of just killing the superconductivity, for example, the yellow region here, the boundary, when you apply the in-plane field, you may kill the superconductivity, the conventional one. However, you can end up going to another state which with the finite momentum. So then it enhances your uppercutting field because you need to. This is still in the superconducting state. And then the one feature for the FFO state is such an upturn in your uppercutting field. Of course, other mechanism can induce this. So one needs to check, for example, that you have really like a clean superconductor. If you induce some disorder, you may kill this upturn and also some other then secondly, you need to check that there is a first order phase transition across this boundary. So usually there's some dynamic evidence with like heat capacitance measurements to demonstrate this. And finally, one really want to prove this, you need to really go to measure, like if you have this especially if you have some modulation of your order parameter. But this is, I think, so far nobody has done this. It's very hard to check this. And what is this related to the niobium diselenide? So in niobium diselenide, we talked about single layer just around the K and K prime points. The spins are just not out of plane. So if you accept that picture, then now let's think about like two layers. When we apply the in-plane magnetic field, the in-plane magnetic field cannot do anything to your Zeeman splitting because effectively your Zeeman G is just 0. You cannot have any Zeeman splitting anymore. So what it does is that the magnetic field can go into your K, so that you can have this vector potential, and that vector potential goes into your momentum. So for two layers, then the vector potential actually points to different this Q corresponding Q of this vector potential points to different opposite directions. So that means within each plane, you still have 0 momentum, but relative to each other, the upper layer and the bottom layer, they have a shift in momentum space. So this is also finite momentum. There is a finite momentum in there. So because of this finite momentum, people also call this FFO state. But the origin of this is not Zeeman splitting anymore. So this is why they call this orbital FFO state. And why is this related to the effect? Because they argue that, again, if you have FFO state, you should be able to see upturn, and they indeed observe this upturn. And then they have also some other effects, which is included in this paper, but also now they do a very careful two-axis rotation so that from this experiment, they observe some six-fold symmetry when you go into this, they claim it's orbital FFO state, which is not the case when you are in this uniform Ising superconductor. So basically what they're doing is they measure how the uppercutting field responds to your in-plane field. And if you're here, then it's isotropic. And if you're here, then it shows you some kind of six-fold symmetry. So they argue that so these features are somehow consistent with the expectation for orbital FFO state.
So could you say again, so there are red dots and then there are gray dots on the phase diagram?
Oh, yes, so these red dots are just from resistance measurements. They determine where they show the transition was when you increase the field.
Resistive transition.
Yes, resistive transition. And then these blue dots, they measure the critical current. And then they observe that along this point, there is a bending of the critical current.
Bending?
Yeah, when you apply the field, the critical current does not just drop down with the in-plane field, the critical current drops, and then there's a kink. And then it drops further when you go to a higher field. So then they mark out this kink as the phase transition line.
So is there any hysteresis that supposedly first order?
So I wish you already that. Recently we got something and we believe it's first order transition. Yes, so just in a minute.
So this effect, why do we have this bend? It kicks up in only at higher with lower temperatures.
So the
why
argument
doesn't it go all the way?
Yeah, so the argument you transitions to another state, and this state helps you to boost the critical current. So critical current drops down like this usually. And then up to this point, you go into another state, so the critical current can survive for a larger field. So then it gives you a you plot the critical current as a function of. So recently, what we did is we fabricated the sample, niobium diselenide, and we tried to measure the tunneling spectroscopy by using tungsten disulfide as a barrier and graphite as a metal electrode. And what we see is that when we apply the B field in the plane, from around 6 to 7 Tesla, the gap actually becomes a bit enhanced. So like here, we zoom in here, that we see that around 6.1 to 6.7, the gap actually becomes stronger. So this is somehow related to the transition. And now if we plot this, now maybe stay at zero bias and just plot the tunneling conductance as a function of the in-plane field, then we see the first order transition. So at low temperature, we do see some hysteresis. And this field is the field where the upper critical field shows upturn. So somehow it's consistent with the expected first order transition. And also, this is not perfectly aligned to the in-plane. If we really apply to the in-plane case, we see that there's really some jumps when we around this transition point. And this is very sensitive to the in-plane field. If we tilt it just about 0.1 or 0.2 degrees, then it's not very clear. So within 1 degree, then it disappears. So
you don't think like flux lines could explain the jumps?
The flux lines cannot explain why it happens exactly in this field.
Yeah.
And we also compare this. I don't have this data here, but we can discuss later. So this is just one sample, and the phase boundary is here, which matches with this upturn point. And we also change to Seeker samples, and then the phase boundary just goes down.
Yes. I know.
So, I mean, for these samples, the starting point is a bilayer with the in-plane field introducing some vector potential to shift your momentum. Now we have many layers. So then our theoretical collaborators just gave us this picture that, again, this is just shifting one by one. This is a bit different from what the other group in the beginning claimed, that you have opposite shift in between the layers. Here, we believe the momentum shift is just uniform, just monotonic. So for example, this layer, the layer lower below shifts to the right-hand side, and then the other one shifts further to the right-hand side, and then etc.
So an intuitive understanding why such a transition between the momentum states should be first order.
I think there is some mismatch in the gap. Okay, maybe that's just from our data. It's not really helping. So most of these transition from uniform state to some kind of modulated state is first order. Yeah, but I think I don't know, and I have a big intuitive picture.
So I have a question. I thought Eisen superconductivity was supposed to be strongest in the monolayer because you're breaking in-plane mirror symmetry.
Yes.
But you have 3 layers?
We have here is 25 nanometers, so it's one of these.
So I thought it's
yes.
bulk
It's
sample.
already quite
there
like
is
about
no broken in-plane mirrors.
This is also why I think this paper, the first one when they claim orbital and the no, this paper is kind of shocking or interesting because nobody thinks in the bulk limit, like 22 or 34, will do something interesting. But I think for each of the layer, you still have say this icing area. It's just weaker, but it's still somehow there. So they say that the globally it's inversion symmetric, but each of the layer is a break.
So I'm just going back to the Zhang and Mark papers.
Yes.
I thought that as they increase the number of niobium diselenide layer, their upper critical field fell well below the Pauli limit, so they said Ising had disappeared. So you're saying that's not true?
So actually, even in the bulk, it can exceed the Pauli limit a little. And here you see that it exceeds the Pauli limit by just this much. So just from that point of view, let's say still has some Ising. I think this is so far all I want to say about Ising. Let me just quickly go to the next one. These things I will just skip. This is just going to the bulk.
Can I ask one more question? Sorry about your previous work. You had tungsten diselenide as one of the.
Yes.
It's spin orbit coupling.
It's very strong. Yes, I know.
Does that impact what's going on in your sample?
Our argument is, I mean, first of all, we try to look at it, but we don't see a very clear feature. Like from the transport, we are moving. So the transport data, we actually are measuring not in this region where we have the constant disulfide, and that matches well with our tunneling data. Yeah, I guess that's, and also we try to think about this orbital matching thing, and because we do not align these flakes in certain direction, so there is a large. I mean, the orbitals they do not really overlap, so I think the effect could be very small. Okay, so maybe a quite quick summary. So I think so far we see the largely enhanced upper critical field. The gap can decrease continuously, and there are some two-fold symmetry or six-fold symmetry related to some nodal phase in this system. And for multi-layers, then there could be orbital FFO state, and also if you have some intercalation or some special stacking, then you can have also the Ising spread.
Just to make things clear, it's only in multi-layers if you have thinner layers.
You mean for intercalated system or
the FFO?
For FFO, the quality of the flake drops down very fast, or then becomes not easy to see this.
It should be there. There's no reason why.
Yes. So initially the prediction was for 5A. And I forgot to mention also in one group in Stuttgart, they measured intercalated molybdenum disulfide. They also observed some upturn. They claim this is maybe to So anomalous metal phase. The feature of anomalous metal phase is quite simple. That when we measure the resistance and during the superconducting transition, usually if you go to lower temperature, then the resistance just drops to zero. And when you apply the field, the transition just shifts to lower temperature, but then in the end, it should drop to zero. But for some systems, many 2D superconductors, they show that the transition actually does not go to zero. It saturates at low temperature. So this is the feature that people claim to be anomalous metal phase. And now even in, for example, high temperature superconductors, when they dig these holes to mimic Josephson junction arrays, then they also see this is without field, just by changing the holes, the size of the holes. Then they see also the saturated resistance after the superconducting transition. And why is this strange? Because usually if we estimate here like this normal resistance, if you have some normal resistance, if you argue that this is just because we have some region that never superconducts, and then you have some region that superconducts, then from this resistance we can estimate the size of the almost this region that never superconducts. And the size is so small that the superconducting region should induce superconductivity in this small region via the proximity effect. So that means that even if you see some kind of small resistance, then at low temperature it still should go down to zero due to the proximity effect. But this is not the case for many of these systems. So this is also somehow have been seen in many of these crystalline samples. It was first seen in these amorphous films. So for niobium diacylindide back in 2016, this is somehow back to back with the other paper about Ising superconductivity. When they measure the bilayer, for bilayer they also see a very large in-plane upper critical field. But also when they apply the magnetic field, you see that when we plot the resistance with the inverse of temperature, then we see some saturated value after this transition. So this is claimed to be the amorphous metal phase in a highly crystalline.
So this paper was retracted by Bashupati.
It was not retracted. They did a correction to make it move.
Okay. There is a debate, but I think the data is valid.
I'm not an experimental scientist.
Since you're there, actually, I think he remeasured some of these.
You mean Benjamin Hart or
Benjamin Sasepe? So there was a subsequent paper, I think maybe even with the same sample in Grenoble.
This one.
Yes, I think so.
Yeah, this is the filtering versus.
Yes. So when I first saw this paper, I thought, okay, everything is over, right? Because this paper just showed that niobium diacylindide, the same sample, when you filter it or not, either you see it or you don't see it. So you have the saturated resistance if you don't have good filtering, and if you improve the filtering, then you can kill this effect. So this looks like the so-called anomalous metal. Yes.
Sorry for the non-experts. What is filtering?
Filter is you add some low-pass filters. So you can have, for example, some RC filters, and also you can for dilution-free use you can have these thermal coax cables, so that can filter out all the high-frequency radio frequency signals.
But still, some groups observe the saturation even after filtering.
Exactly. So I will also mention that part. Yeah, so the thing is for niobium diacylindide, after this paper, the people become very careful about filtering. And for example, this YBCO paper, they also, this is very high temperature, and they also carried out this with filtering, and they still see this. So somehow, this radio frequency noise cannot explain everything. And there is a follow-up paper, also from I think the same group of people, and they compared monolayer with four-layer system. What they are trying to say is that you see it here in this blue region, it's really zero resistance. This is a zero resistance state, and then when you increase the DC current, because previously people showed that even with the filter, if you add some DC current to the system, you can also generate some kind of saturated resistance. Looks like because you heat up the system, the electronic temperature becomes high, so that even if your nominal temperature goes down, actually your sample temperature does not go to that low. But they say that this DC current effect is there for four-layer. For example, if you cross to this blue line, crosses the dash curve, then you go to the system with some final resistance.
Do you happen to know whether the anomalous metal state really has or how constant does this resistance become? It sure looks constant, but is this because we compared something very steep? Or is it really, if we zoom in, will it have a slope? For example, for the first micron passage?
There's no slope. Yeah, it's just a flat. However, in this paper, they just want to claim for monolayer, you cannot see a clearly defined region with the zero resistance. So just with a small, tiny little DC current, you suddenly go into this finite resistance regime. So what they are saying is the model is somehow special, that is very sensitive to some perturbation, some disturbance. So I would say that after so many years, then still people are interested in this niobium diselenide setup. So they just treat the system, okay, no matter the reason is either it's extrinsic or intrinsic, but it's there. The final resistance state is there. Let's just measure something more. So for niobium diselenide recent work, they measured a trilayer niobium diselenide. And first of all, this was already done in amorphous films that in the anomalous metal phase, when you measure the Hall resistance, you don't see the Hall signal. So that's somehow showing that you have particle Hall symmetry in the anomalous metal phase. Then this is also seen here in their sample for either a bilayer or a trilayer. You see that this is the blue curve shows you final resistance when you apply some field, and then the orange curve shows that they don't see Hall resistance up to this point. So within this range is the anomalous metal phase, but you don't have the Hall coefficient. You don't see Hall effect. So it's like particle Hall is symmetric. And first of all, what they measured is they use Raman spectroscopy, but they cool down to very low temperature into the superconducting state. And within the superconducting state, they see a mode appearing, which is related to the Higgs mode, so the amplitude mode of the autoparameter. And this is in the bulk. You can see that either with temperature, you increase temperature to about the initial temperature, this mode disappears, or you increase the field and to kill this mode. So this is related to superconductivity. And for the bilayer case, the interesting thing is, if we apply some small field, you go into the anomalous metal phase, do we still see the Higgs mode or not? So what they are claiming is by going into the anomalous metal phase, when the resistance here, you have finite resistance, you have the Higgs mode. So that is to say that within the anomalous metal phase, you still have this Cooper pairs. The Cooper pairs give you the Higgs mode. So what they are claiming is within the anomalous metal phase, it has the fluctuating Cooper pairs. So this is another recent development in this direction. I think so far there is no agreement on the theoretical, precisely topic theory about the anomalous metal phase. So one proposal is they claim that it's about the bodies. Think of the system as some randomly connected superconducting puddles, and then the vortices they can jump around when you apply some field, but you have to cross some barrier at high temperature. But when you go to very low temperature, then you go into a regime where the vortices they just tunnel through this barrier. So because of this fact, then you do not have a very strong dissipation. However, when your vortex move, actually it generates some resistance, it generates some voltage. So this is one theoretical picture to understand the anomalous metal phase. So actually, next week I want to mention this, that recently we also measured this to a very thick film, lithium intercalated titanium diselenide. We see the anomalous metal phase. We claim it. This is still 2D, although it's very thick, but from the anisotropy it shows 2D behavior. What we observed recently is the superconducting gap still persists in the anomalous metal phase. This is with 0.1 here, 20 minutes now, this goes into the anomalous metal phase. And in this anomalous metal phase, we still see the gap and it's symmetric. We try to say it's consistent with the picture that you have electron hole symmetry. And another recent work, they measured lead on silicon. And this is interesting because they try to combine transport with STM, so they measure everything in vacuum. So in the anomalous metal phase, they observe these vortices. So what they're trying to say is that, okay, the picture says the theoretical, just last slide, we mentioned that you have these vortices tunneling. So these vortices should be moving around. You don't see, you shouldn't be able to see any stable vortex, but they observe this. So this is experimental fact, but how to understand this, I mean, this is pretty new, so I think there's still something going on.
Is the scale?
Sorry.
Could it be just moving but smeared, of course?
They are pretty stable, so
see the
yes, so you mean like shaking oscillation. I think one thing is that they are arranged in a very regular shape instead of if they are moving around, then you don't see this very regular lattice like. Oh, if it's just like this, then it does not follow the theoretical picture. They should really move around to generate some binary distance.
So all these are, the transport is done with the proper filtering, so we are sure that...
Not all of them. So like in our case, we do filtering, and for this one, they also use filtering, and for this one, they don't use filtering. But then they say, okay, even it's something extrinsic, it shows all the features that other people claim to be intrinsic.
If you're already coming back here, I'll disturb you once more. And something I don't understand about this experiment. He showed the picture of the device, which looks like a transport device. And here they're doing Raman. So they're doing Raman and transport on the same device. What exactly is...
Yes, I think so. They're doing the same thing.
So that's an in situ measurement, which actually has optical access? It's
yes, I think so.
There must be, though. By definition, there's no filtering because it's exposed to an optical channel, right? So that's kind of radiation.
Yes, the radiation is there. Yes, but I mean, from the usual actual wires, I think there they don't do any extra frequency.
Right. Okay. Well, optical is also high frequency.
Optical.
No, I agree.
Maybe I just conclude this part. So these are the features we have talked about for anomalous metal phase. Also in albion diselenide, whether it's intrinsic or not, I think most people think this is extrinsic, but still it's quite interesting to look at it. And then, yes, so maybe a few minutes, I will just skip this, because these are just topological insulators in the 2D limit, the smaller layer, and then they claim they could observe the quantum spin Hall effect, and then when they inject more charge, inject a lot of charged electrons, then they can go and this system becomes superconducting. So, as the title says, this is a superconductivity in a monolayer topological insulator. So this is a topological insulator that can superconduct, but that doesn't mean it's a topological superconductor. There is some feature here that they claim to be a coexistence of H state and superconductivity. But this H state is, as I just learned this morning, so this H state, I mean, it's a conductive H state. It's not really conducting heat. It's not a neutral, charge neutral state. So these are something. And also this one shows both anomalous metal phase and the IC or large optical field. So staining is very similar. So staining is calculated to be topological and shows superconductivity. And people also observe from STM some H states from these islands, and in the middle they see a superconducting gap. So this is again for existence of superconductivity H state. Its band structure tells you it's topological, but it's not really topological superconductor. Okay, cuprates. How many minutes can I have more? Maybe 10. Okay, so cuprates, the story is a bit complicated. So over the years, people try to exfoliate cuprates down to a monolayer. Many of these studies they couldn't see superconductivity in the monolayer. And then they try to conduct this film. They can see superconductivity with transition temperature 70K. In the beginning, they claim this is a dimensionality effect. When you get thinner film, thinner flake, you use TC. However, people realize later that this is just because of doping, because this system is very sensitive to oxygen in the crystal. So then people improve the sample, and eventually, Zhang in Fudan University, they end up having monolayer, so a half unit cell sample with the same TC of the pulp. And also they studied, for example, STM or other things. So actually, quite some years ago, we started to do this because we wanted to address this problem that if you have a twist between the two cuprate flakes, because the cuprate has a natural insulating layer, so we can address it tunneling. And if it's D wave, then the symmetry argument tells us that there shouldn't be any Josephson tunneling, and if it's S wave, there could be Josephson tunneling. And we tried this by just doing the exploration. I mean, people did this before, but with bulk samples, and we just try to revisit this issue with now with the exfoliated flakes. And we see even at 45, we see the Josephson tunneling. It's comparable to either 0 degree or 90 degrees, and we also measure a lot of samples, and we in the end statistically we see. I mean, this is in underdoped regime, but we see that's kind of comparable. So either 0 degrees or 45 degrees, we see the Josephson tunneling. However, then there is this prediction that the magic angle for twisted cuprate is at 45. That means you have D wave in one layer, you rotate one of them 45 degrees, it becomes very similar to this DXY order parameter. So that you can have, if the two layers couple together, treat this whole system as a whole, as a single block, then it has a new pairing, a new order parameter, which is D plus ID. So this is actually topological because it's first of chiral, D plus ID and D minus ID, and it also opens a gap in the spectroscopy because D wave actually has a linear dispersion. It cannot touch the gap is not opening all the momentum space. But now because of this pairing, that you open the full gap in your in your dispersion. And people predict that around 45 degrees, you can have this topological superconductivity. So if this is proven, then this can be the very system with very high temperature, 90 Kelvin. Maybe not really exactly 90 Kelvin, but if you go a little bit, maybe 80 Kelvin, you can have a topological superconductivity. And also it's 2D because you just need 2 layers. So there are some predictions for this. One of them is once you have 45 degrees, you don't have the Josephson tunneling for D wave first order tunneling. But why we are seeing this Josephson coupling between the layers is because we have higher order tunneling. And this higher order tunneling comes with charge 4E instead of charge 2E. So this is one prediction that if we see charge 4E instead of charge 2E, then it may correspond to topological superconductivity, or to somehow they call this time reversal symmetry breaking superconductivity. And
also not many reasons for 4E, right?
Yes. So then I will just show supporting evidence and also something we are doing that trying to disprove this. So Shapiro stamps also. So this is the experiment of Philip King's group in Harvard. So they are claiming that this time reversal symmetry breaking superconductivity when they do this twist. So first of all, they observe some very strong separation of the Josephson coupling around when you go from 0 to 45 degrees, which is different from our observation. We don't see such a large separation. And still, but still around 45, they do see some coupling, and then they claim this coupling is coming from this D plus ID. Because of this D plus ID, then they observe this Shapiro stamps between the integer numbers. This is Shapiro stamps at 1/2 and -1/2. Also here something at 3/2. So with these features, they say, okay, now this is consistent with the expectation that we have charge 4E. So it changes your HF over 2E to HF over 4E. Another thing is they observe some Josephson diode effect. This is not really the standard definition of the Josephson diode, but it depends on how you prepare the state. If you prepare the state in a sense, you go from high current back, and then you sweep the current, you have a critical current, which is smaller than the current when you go to the negative direction and then do the sweep. So this is after this paper, then theoretically they claim that this is consistent with the expected behavior for D plus ID, because D plus ID breaks time reversal symmetry, and then you are not exactly at 45 degrees. This is around 40 degrees. So then you also break the inversion symmetry. So you satisfy these two conditions, you have some diode effect. So the current is not symmetric.
Is the change in current related to the trapping current?
No. This is not,
if
these
the
are all
trapping
going
current
on.
is higher,
Yeah.
is the change larger?
The trapping current is not influenced by this. So only the current.
What I'm thinking is a sort of a heating effect. In
Oh,
one case,
okay,
they come and they stay longer.
Okay.
In the superconducting state, in the other one, they stay shorter, and the higher the trapping current, the shorter they would stay in this. They would have to cool down.
What we can see is either you sweep this way, here you have a higher current, or you sweep from here going back to zero, and always going back to zero, and then you sweep, you have a smaller current. Yeah, so there's no heating. At least for this reading also, you go to the zero resistance state, and then there's no heating. So then you have a jump. So their argument here I just so the argument is you have usually you have the washboard potential for the Josephson effect, but due to this higher order coupling, then each of the quantum well becomes has a double minimum. So then you can have different preparation because you have either the phase particle in one of the minimum or the other. So that gives you different video current. So now let me show something against this picture. So we first of all we tried many samples, and we could see that the critical current has a quite conventional behavior, not as expected for theoretically calculated for this D plus ID. So D plus ID with higher order pairing, so the critical current, the temperature dependence should be different, but it's not the case. We also checked the Fraunhofer pattern, and we don't see this H over 4E appearing when you change the temperature. And also the Shapiro standard, I will skip this, but this is just to show King's data and our data. We measure several samples, and we don't see really like half integers. We do see in one sample half integers, these features 1/2, 3/2, but for the same sample, if we just do several small cycling, then there's no more. So we believe these are just some trapped vortices, and that induces some effects. So we actually apply the field, a little field, we could also induce some half integer Shapiro stems. Yes.
How high do you go with this? So say thermal cycling, this
just above the TC, just 90 Kelvin. And this is just the final page. So diode effect, we could also induce a diode effect in the sample if we apply some current pulse. And it's very reproducible. We introduce this diode effect where it's asymmetric critical current. And if you just raise the temperature above TC, cool down, you can go back to this symmetric case. And you send the current pulse, you can again have the diode effect. So the take-home message is, I think one needs to be very careful of these trivial effects that could induce the same results that is claimed to be topological or non-trivial. Yes, so let's just summarize. So for constant dynamics, then it's just a coexistence of H state and superconductivity. And for twisted cuprate, theoretically, it's very nice. It's a high temperature 2D topological insulator, superconductor. However, so far there is quite some debate whether this is true or not. So, yes, finished.
Few more questions?
Concerning this 45 twisted disco junctions. So I understand if you suppress the first harmonic of the chemical isolation, then you are left with these 4 returns.
Exactly.
But this you have in any highly transparent Josephson junction.
Exactly.
Why is it? What is the evidence then for the unusual pairing?
I think the one thing is it's still the insulating barrier is still there, so we are not changing the transparency, or it's very hard to change the transparency of this junction. And also, it still shows a very strong hysteresis. So it looks like it's still a SI-S junction instead of going to the S and S junction.
But then you should completely suppress the supercurrent if you have no second harmonics.
If I have no.
I mean, if it's really a tunneling barrier and second harmonics is vanishingly small, then no supercurrent is left.
For D-wave, yes, right, yes.
So that you have still something that remains shows you that there is apparently enough coupling for the second harmonic. If it is nominally tunneling, 14 holes or whatever.
But not necessarily second harmonic, because we believe the first order tunneling is still there. So which is not easy to understand if we just think about purely D-wave. We are trying to say, okay, there is an S-wave, which is more straightforward. Then nobody likes it.
Okay.
There are really few groups who are able to handle Discord to make it like monolayer and bilayer. So it's like a old kind of story with cryogenic stage, exposition. How did you manage to actually do really think layers to be able to do this twisted?
Also, for the twisted cuprates, so far it's not very simple. So it's on each side it has in our case minimum 30 nanometers, so 10 unit cell.
Okay, so it looks like that you don't care so much under the surface.
Oh, and then we need to cap it with boron nitride before we take out from our. Thank you.